we call it a Hubert space. Okay? So what is a Hubert space? Well, it's just a Banach space where the norm comes from an inner product. Okay? You may have a situation where you have where your space is just a norm vector space, but not complete. Okay? This is not a Hubert space. Hubert space is a Banach space where your norm comes from the inner product. Comes from an inner product. Okay, so be a little bit careful when you think about this. Not all Banach spaces, it's not always the case that the norm comes from an inner product. This is a special structure that you are adding to the norm. Okay, so when your norm comes from an inner product like this, you call this a Hubert space. So the basic example that you should have in mind, the basic example of a Hubert space is our L2 of any measure space. You know, if you have a set, a sigma algebra, and a measure, the space of functions that we call L2 is a Hubert space, right? We have proved that this is a Banach space. And we have seen that the norm, we have defined the norm L2 as being this, right? Well, and then the inner product would be just the integral of f, g, let's put g bar if you're working with complex valued functions. So this would be your inner product of f and g. If you are working with complex valued functions, you would put g bar. If you are working with real valued functions, you don't even have to put g bar there. This would be the inner product that generates this norm. You realize when you put g equals f, so f inner product f gives exactly this for the norm. Okay, so in some sense, these are all Hubert spaces. Essentially, all the Hubert spaces end up being like this, up to isometry, you know, especially if it's a separable Hubert space. So this is essentially the model that you should have in mind. If we have time, or if we don't get to see in this course, you'll definitely see in the functional analysis class that if a Hubert space is separable, then it's isometric to a little L2. Separable just means that it has a dense and countable set of points in there. Okay. But let's see. Let's move on. So this is introduction, definition, and very basic properties about Hubert spaces. Now I want to discuss with you topic number 2 of today about projections. Okay. So you are there, you know, minding your own business, you know, you have a Hubert space, you have a norm, you know. Every time that you have a space H, Banach space with a norm, you know, this is a metric space. You know, you can define just the distance between 2 points as just being norm of x minus y. Okay, a metric is a distance that verifies roughly the same properties of the norm, right? So the distance of x to x is 0. The distance of x to y loses to the distance of x. So you have a triangle inequality here. Okay. Do I need anything else? No, I think that's fine, right? And the distance function is always non-negative, right? So this is every norm space is a metric space. Yeah, okay, maybe you're right. Distance of xy is equal to the distance of y. That's fine now? These are kind of, so whenever you have a space with a distance here, you call it a metric space, you know, and you can do, you know, this metric space has a basic topology on it, you know. So you can define the ball of center X and radius R as the points Y in your space, say H, such that the distance of X to Y loses to R. So every normed vector space is a metric space, but the converse is not true. I mean, a metric may not come from a norm. Okay, so this is some concepts that you should have in mind. Sometimes a norm may come from an inner product. So this is a stronger concept. Sometimes a metric may come from a norm, but really a metric on its own doesn't need to come from a norm, and a norm on its own doesn't need to come from an inner product. But if you are in this environment that you have a normed vector space, this of course has the usual balls and has the usual topology associated to it, okay? That we call the strong topology. So when I say something is converges in this set, or something is closed, or something is open, you can really define the open balls just like this. So this would be the open ball on a normed space, and it's topology generated. And the open set is just like in the Euclidean space. So what's an open set in a normed space? In the strong topology, well, for any point in that set, you can put an open ball inside the set. Okay, so this is the topology generated by these open sets. It's called the strong topology. And the complements of the open sets are the closed sets in that space. So now, I want to consider the following situation. So let M contained in H, so H is our Hubert space, let M be contained in H, be a subspace, be a closed subspace. Subspace, everybody knows what it is. It's a vector subspace. Sum of guys in M is still in M, and multiplication by scalar is there. Closed, this subspace is closed in the strong topology, in the sense that a sequence of points in this space converging to a guy, this limiting guy will be in the space. Now, if you are in RD, every subspace of RD is obviously closed if you are in a finite dimensional space. But Hubert space, the magic of it is that they may be infinitely dimensional. And if you are in an infinitely dimensional Hubert space, there may be subspaces which are not closed. Okay, think about it. For example, even inside L2, okay, if you take L2 of R, the continuous functions form a subspace. Sum of continuous functions is continuous, but the continuous functions are dense in L2. So they are a subspace, but they are not the whole space. There are functions in L2 which are not continuous. But if this subspace were closed, if you take the closure of this would give the whole subspace. So this subspace is not closed. It's dense, but then hence it's not going to be a closed subspace. Okay, and many other examples that you can come up with. But now, so take an M, a subspace, closed subspace, and then you take a point X outside of it. Okay, so let X be a point that belongs to H, not in M. I want to define and to study the distance from X to M. Okay, so I'll let the delta be the distance from X to M. Well, the distance from X to M is just the infimum of X minus Y with Y belonging to M. Okay. I put here an infimum because I'm not sure this point actually is attained. This distance is attained in a point. But the distance from a point, this is a definition in general. The distance from a point to a set is the infimum of the distances X to Y to points Y in that set. Okay, good. So if M is a closed subspace, I want to study this. I want to prove that this is actually well-defined. It's attained, and it's uniquely attained in a point that we call the projection of the point X in that subspace. Good. But before I go in that direction, let me let me define this other subspace. So let's define the subspace that we're going to call M perpendicular, to be the points y in, let's call the points z in the Hubert space, such that z is orthogonal to y, okay, for any y in M. Okay, so just note, when you have inner product of two guys being 0, we say that these two elements, two, are orthogonal. Okay, we say that two elements are orthogonal when their inner product is 0. If I fix a subspace M, the M perp will be the collection of points in my Hubert space that are orthogonal to all the guys in M. So it's very easy to see that this M perp is also a subspace. Right? So if you take Z1 and Z2, if Z1 is perpendicular to all y, Z2, of course, you can add them up and you can multiply by scalar. So this guy ends up being also a subspace. So in the representation would be perhaps something here, M perp if you want. Okay, so let me prove now this proposition 3. And this is something about projections. Okay. Just see that I don't forget something. Let's see. Okay. So let M be contained in H be a closed subspace, and X be a generic point in H. So I'll make some claims. There exists a unique point. There exists a unique point, let's call it Px, that belongs to M, such that the distance from X to Px is equal to the distance from X to M. 2, there exists a unique decomposition of X as, you know, X being Y plus Z, with Y in M and Z in M perp. There exists a unique way to decompose X as a sum of two guys, one in M and one in M perp. So just in this case, this Y that appears in this decomposition here is going to be your projection of X, your P of X of the previous item. And let's call this Z Q of X. Part 3 is you have Pythagoras. X square is going to be P of X square, so these add up. And part 4, the maps that you just created that sends X to P of X and that sends X to Q of X. So these maps are linear maps. Okay. What I'm trying to say is that I'm trying to define if I have a closed subspace and a point outside, what is going to be this projection of x over the subspace. It's the point in the subspace of minimum distance to x. But it's also going to be it is also going to be such that x minus p of x is going to belong to M perp. So x minus p of x is going to be orthogonal to x. So this is what the geometry tells you in high school, right? So if you have a point outside a plane, there is a point that minimizes the distance, and this line is orthogonal to the plane. The same picture applies to Hubert spaces here. These things that I'm telling to you today, they might be very simple, and they are actually very simple in the general setting. So the nice thing is to actually recognize the structures of Hubert spaces when they appear in front of you, and to properly use these theorems. It's very beautiful. So let's see. Perhaps one fact that I should have mentioned to you that we are going to use throughout this proof is what's called the parallelogram identity. And this is essentially this. Let's see. So this is when you take two elements on a Hubert space, and you take x plus y square, and you add up with x minus y square, I believe this gives you 2 times x squared plus 2 times y squared. The proof is straightforward. So x plus y squared is just x plus y, scalar x plus y. And this is x squared plus xy plus yx plus y squared. And the other one, x minus y squared, is x minus y, scalar x minus y. This is x squared minus xy minus yx plus y squared. And you just add up these two. Cancel this, and this, and you get your identity, okay? So this is very innocent, but it has a lot of power. Let's see. And again, this holds in any Hubert space. So let's prove our claims about projections. Okay. So the first claim that I made is that if you have a point, if you have a closed subspace and a point, any generic point in your Hubert space, there is a unique point that realizes the distance. Okay? So there are two things here to prove: that there is actually a point that realizes the distance, and that this point is unique. So part one. Okay? So the first thing is that if your point x belongs to the subspace, well, there's nothing to do, right? So then let's call this delta, which is the distance from x to m. Let's just call the distance from x to m to be delta. This is going to be 0, and the only point in the space whose distance to x is 0 is itself. Okay? And we have nothing to do. Projection of the point is himself. Okay, so if not, now if your x does not belong to the closed subspace, then this distance here, delta, is actually bigger than 0. If your point is not in the subspace, then the distance to the subspace is bigger than 0, strictly bigger than 0. And this is because it's a closed subspace. If the distance were not bigger than 0, if the distance kept being 0, remember, the distance is the infimum. So you could find a sequence of points y in the space such that the norm of x minus y would approach 0. In other words, these y's would converge to x. Since it's a closed subspace, this x would have to belong to the subspace, which is not the case. So if x does not belong to the subspace, then this distance is bigger than 0. Okay, so now what you do is that you don't know that this distance is realized. That's what you want to prove. So let the Zn be a sequence of points in the space such that the norm of x minus Zn converges to this distance, which is delta. So you take a sequence of points. This is by definition, right? The distance of a point to a set is the infimum of these things. So if you say that this number is delta, then there will be a sequence of points in your set such that these things converge to that delta. There is a sequence of points Zn in my space such that x minus Zn, the norm, converges to this delta. All right. So I now use this parallelogram identity. Let's see how we can use this. So now use star. If I use star, I can start with this x minus Zn square and put x minus Zm squared. Let's take two guys in the sequence. This is going to be 2 times, take a look. If this is A and this is B, this guy here is going to be A plus B over 2, and this guy here is going to be A minus B over 2. Okay, so if I get A, B, this is going to be 2 times A plus B over 2, so it's going to be x minus the m over 2, plus 2 times A minus B over 2, the m minus Zn over 2. So this is what the parallelogram identity gives me. Now, look how great this is. This, on the left-hand side, is going to what? Remember, this is going to delta. So this is going to delta, and this is going, so as n and m go to infinity, this is going to 2 delta squared. Right? This is going to delta squared, delta squared. On the other hand, the right-hand side is, I'm just going to use the fact that if Zn and Zm are points in the space, Zm plus Zn over 2 is also a point in the subspace, okay? I'm using the fact that it is a subspace. I didn't, even for this argument to work, I didn't actually needed a proper subspace. This same argument works if you have any closed and convex set, okay? Whenever you have a closed and convex set, you can say that the sum of 2 points over 2 belongs to that set, okay? And therefore, this is bigger or equal than 2 times, well, the distance from x to any guy in the set is bigger than delta. So you get delta squared plus 2, okay? When you revisit this point in your functional analysis class in a few months, you will talk a little bit more about closed convex sets in Hubert spaces, okay? Just wanted to emphasize that you don't actually, but for our purposes, subspaces, it's okay for now. So what do you see from here? What's the conclusion that you get? This left-hand side is going to 2 delta squared. The right-hand side is bigger or equal than 2 delta squared plus something. Yes, so the only way that this has happened, that this could happen, that the left-hand side goes to 2 delta squared and the right-hand side is bigger or equal than 2 delta squared, the same number, plus somebody, is that if this somebody is going to 0, okay? So in other words, this shows that, hence, this sequence Zn here is actually a Cauchy sequence. Right? This has to be going to 0 as m and n go to infinity. Otherwise, you would break this inequality. Okay? Now, if this is a Cauchy sequence, and remember, we are on a Hubert space, which is a complete space, right? So then, this Zn converges to a certain Z. And because your set is closed, this Z has to belong to the set. Okay? And now, since x minus Zn, this was going to delta, at the limit, you know, This implies that x minus z has to be equal to delta. Okay? Because obviously the norm map is continuous. So we have proved the existence of a guy in the space that realizes the distance. So we have constructed a guy Z in M that realizes the distance. Now, what about uniqueness? Well, uniqueness is simple, right? If you had Z and Z prime such that realizing the distance, let's say realizing delta, you could use again the parallelogram inequality, the parallelogram identity, right? In the same way as it's written there. So x minus z square plus x minus z prime square is equal to 2, and then x minus z plus z prime over 2 square plus 2 z minus z prime over 2 square. But now this would be equal to delta square. This would be 2 delta square. And this again would be bigger or equal than, because this is a guy in the space, so this would be bigger or equal than 2 delta square plus 2 z minus z prime over 2 square. 2 delta square bigger or equal than 2 delta square plus somebody. The only chance that you have is that if this somebody here is 0. So the only chance that you have is that z is equal to z prime. So if you have two guys realizing the distance, they have to be the same. So in fact, you have just one guy realizing the distance. So we call this z that we constructed here, we call it p of x, okay? All right, so this goes for part 1. There is one guy, it's unique, and we call it p of x that realizes the distance. And I already have used this very innocent parallelogram identity twice to prove this. Okay, so don't underestimate the power of easy things. This is one thing that you have to learn from this course. Don't underestimate the fundamentals, the easy things. So if you really get the good and solid background on the easy and basic things, this is what's going to move you forward, you know. I remember when I was in high school, I played basketball. And the coach of my basketball team, he was a guy just like this. He wanted us to do the fundamental and basic things, you know. So passing the ball would be just like this, you know. You pass the ball and you leave your arms a little bit forward, you know. And whenever in the game, we were playing the game, somebody would get the ball and did this, the guy would stop and say, "What the hell are you doing? Passing the ball was like this. I mean, we don't do this, we don't do that." Same thing with the layup. The layup, right? So would go layup, say 1, 2, and all in the basket, right? So we did it 100 times a day, 1, 2, and then somebody in the game would do the same thing. He would come alone in a counter attack, and just the basket, and the guy would come, wow. And then the coach would stop and say, "What the hell are you doing, man?" So that's what I'm thinking. So just get the fundamentals right, and then from that, you can go wherever you want. Same thing applies here. Okay. Okay, we are going to number 2. So now I want to show that there is a unique decomposition of X as a sum of a guy in M and a guy in M perp. Remember, M perp is the subspace of guys which are orthogonal to everybody in M. Let's go, part 2. Let's first prove that such decomposition has to be unique. So if you had 2 such decompositions, if you had X equals to Y plus Z equals to Y prime plus Z prime, 2 such decompositions, what you could do is, well, you just take Y minus Y prime. This would be equal to Z prime minus Z. So this is the same number. But this now belongs to, well, y and y prime would belong to M, and hence the difference belongs to M because it's a subspace. Z and Z prime would belong to M perp, hence the difference would belong to M perp since it's a subspace. But then it's very easy to notice that if you have a subspace and the perp, the only guy that belongs to the intersection of these two is 0. Okay. You can't have a guy in M perpendicular to everybody in M because it would have to be perpendicular to itself. So X inner product X would have to be 0. This point X would have to be 0. So then Y is equal to Y prime, Z is equal to Z prime. This is very clearly the uniqueness. Okay, so now let's prove that the decomposition exists. And the hint is kind of given here. Well, to do such decomposition, you'd better take your Y being P of X. Okay, so now let's prove the existence. So let us take my Y being P of X. So all we have to prove, okay, so then we need to prove that, well, that X minus P of X belongs to M perp. Okay, this would be my Z. If I take this guy, I just have to prove that this difference belongs to M perp. Okay, in fact, let's do it. In fact, let Y belong to M perp. Not Y, maybe I should call it another. Maybe let W belong to M perp, be any guy. Be a vector. Okay, let W be a generic vector in M perp. Let's just assume that W has norm 1. I can always dilate and assume that the norm of W is 1. Let's see, I want to investigate this thing. So let's say X minus, let's call it this X minus P of X. Let's call it Z. Tell me. Yeah, okay, yeah. I'm assuming that that's true. If M, because if M is the whole thing, then in case I actually already treated this case, right? But you're right. Yeah, in case M purpose, in case M purpose is not 0. So I want to show that this Z is orthogonal. This Z belongs to M perp. So I want to show that it's orthogonal to any element of M perp. I will take a generic element I'm calling W, but I'm going to assume that W is 1 in norm. And I want to do Z scalar WX. Is this what I want to do? Give me 1 second. So what do I want to do here? I want to show. Oh, I'm sorry. Let me take a step back. So I am going to take this Y being the projection of X. That's fine. And I'm going to define Z equals to X minus P of X. And I want to show that this guy is M perp. So this means that it has to be perpendicular to any guy in M. So I want to evaluate Z. I want to show that this is 0. This Z, scalar any guy in W, is 0. But what do I do now? And again, you rule out the trivial case. Of course, if M is the trivial subspace, you're not interested in that, right? Let's see. For this, I would try to do the following. Let's try to do this. Z minus W lambda, scalar z minus W lambda, this is always something that is bigger or equal than 0. Do you guys agree? Now let's open this up. This is norm of z square. And this is going to be minus lambda wz minus lambda bar zw plus lambda square, and then the norm of w that I'm assuming it's 1. So I get modulus of lambda square. So lambda here is a complex number, okay? So get norm of lambda square. So this is actually z square. This is a guy and its conjugate. So this is minus 2 times the real part of lambda omega z plus modulus of lambda square. Again, and this is always bigger or equal than 0. All right. Is this what I wanted? In fact, no. This is not only is it bigger than 0, but this is equal to, z is x minus p of x. This is equal to x minus p of x minus this lambda w square, right? So this is equal to this, and this is bigger or equal than, so p of x is a guy in M. This is also a guy in M. So the difference is in M, and the distance from x to everybody there is bigger or equal than delta. So you get delta square here. But delta square was this. So you really get delta square here too. Delta square was the norm of z. X minus p of x is delta, the norm. So you really get to cancel your delta here, and you get an identity. Well, you get an inequality. Minus 2 real part of blah, 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 plus modulus of lambda square has to be bigger or equal than somebody. Okay? Now it's the point that you have to convince yourself that the only possibility that this is bigger or equal than 0 for any complex number lambda is that if this inner product here is 0. Because if this inner product is not 0, okay, when lambda is very small, you are going to break it down. Because when lambda is very small, lambda is much bigger than lambda square. Okay? So if this is not 0, you will break this inequality for some lambda complex. Well, you have to align. You just call it lambda times this to be real and positive. So you get really minus 2 lambda. And then when lambda goes to 0, you break it down. Okay? So this is the argument to show that this is true. So if the inner product of W with Z is not 0, you can break this inequality for lambda small. Okay. Therefore, the only possibility that you have is that this W with Z is actually 0. So in other words, Z is orthogonal to any element. This W was just a generic element in M. So in fact, this Z has to belong to M perp. So you actually have written this X equals to PX, and we call this Z just QX. So this is a guy in M, and this is a guy in your M perp. All right? And the other parts are trivial in the sense that part 3 part 3, that you have this Pythagoras theorem, that the norm of x squared is just equal to the norm of these two guys, is just because these two are orthogonal. So when you add up two guys that are orthogonal, if you just write what the norm is and you split the inner product, you just get norm of p of x squared plus q of x squared. So 3 is clear because this guy belongs to M and this guy belongs to M perp, okay? And 4, the maps that you have just created are linear. This is also clear from 2, okay? This is also clear from 2. 2 is the statement that you can always decompose a vector x in one element in M and one element in M perp. So if you have x and x1, and you can decompose x in this form and x1 in this form, you have to just add them up. And when you add them up, the addition of p of x and p of x1 is always a guy in M, because it's a subspace. The addition of q of x and q of x1 is a guy in M perp. There you have the decomposition, and you know it's unique. You have proved, so this must be it. So the p of x plus x prime is equal to p of x plus p of x prime. Same thing for q. Also, when you multiply by lambda, p of lambda x is just lambda p of x. This is clear too. So there you have it. You have constructed your proposition. Okay. So we have proved that there is a projection of a guy in a subspace. When you subtract x minus p of x, you get something that is orthogonal. So you get a decomposition. This decomposition is unique, and it's a linear map. And you even have Pythagoras theorem if you want to use. So you can see that we are not. I'm not going to do this because we're not going to use too much in this course. But we are not actually very far to kind of finishing up, or learning a little bit more about the Hubert spaces, in the sense that if your Hubert space is separable, one of the results that you probably will learn in functional analysis is that you have an orthogonal orthonormal basis, And this is essentially applying this interactively, You take if your space is separable, if there exists a collection of points that it's dense in the space, then you just take one of these points. You take the subspace that it generates. You take your point x and you project into that space. Then you take the second point. You take the subspace spanned by 2 vectors. That's your second space, and then you project, and then you keep going with this construction, like a Gram-Schmidt orthogonalization, and this leads up to this decomposition being convergent. If you want to keep doing this to this number. But instead of, I'll spend the rest of the lecture today to prove this Ris Representation Theorem. Going to be very nice. Let's see. Okay. 3. I wanted to, so the final point today, let's discuss some bounded linear functionals. Okay. Here's something interesting that you will get to know more when you do your functional analysis class. So let x, let x be a Banach space. Let's, for one moment, leave the environment of Hubert spaces. Let x be a Banach space. And here you may say over C or over R. Over, let's say over C. You can also say over R. That's fine. A, okay, so A bounded linear functional is just a function, is a map, call it L, that goes from your Banach space R to the field of scalars, C, or R if you prefer, such that so consider the maps from your Banach space taking values in the field of scalars. As the name suggests, it's linear. Okay. Meaning that L of lambda x plus y is lambda L of x plus L of y. Okay. This for any x and y elements of your Banach space x and y and lambda in your field of scalars, complex numbers or real numbers. So it's a linear map. 2, it is bounded in the sense that this number called the norm of L, which is just the sup of L of x modulus, right? L of x, if x is an element in your Banach space, L of x takes values in C, sup of the modulus over all elements x in your Banach space x, such that the norm of this little x is less than or equal than 1. Here the norm is the norm in, I'm going to define Banach space with the norm. When I put this, the subscript here, I'm denoting that this is the norm of the element x in the Banach space, big X. Okay, this is another norm. Okay, but let's just define it to be like this, and I want this to be finite. Okay, so whenever you take your functional and you're evaluating guys that have norm at most 1, you don't blow up. There is an upper bound for this. The supremum of this is what we call the norm of the functional L. Okay? So now, a few remarks about this definition is that remark 1, and I'm going to actually put to you as an exercise, maybe this is the exercise in your homework later on. So a linear map L from X to C or R, if you is bounded in this sense if and only if it is continuous. Okay, so in terms of linear maps, saying that it's bounded in the sense that this number is finite is the same thing as saying that it's continuous. It's a continuous map. Well, you have the topology here. The topology in X is the strong topology that I'm referring to. Is the topology given by the norm. Okay. Think about this, but remarks that I have to do about this definition is the following. And then, so you'll see in books called bounded linear functionals or continuous linear functions. That's just the same. Okay, these are just the linear maps from X to the field of scalars that are continuous. So this itself is a vector space. So the space of all bounded linear functionals is actually a vector space. Okay. You can just take two functionals, L1 and L2. How will you add up the functionals L1 and L2? You have to define them on a point X of your Banach space You just define them as being L1 of x plus L2 of x. You define them what it has to be. Multiplication by lambda of a functional L1, of functional L at a point x is just, by definition, lambda times L of x. Okay? So with these two definitions, this becomes a vector space. Another exercise for you guys to do. This thing here, star, actually, so this vector space we usually called the dual space, and denoted by x star. So if you have x a Banach space, when I write x star, I mean the dual space, the space of bounded linear functionals in x. Okay? So this is a vector space, and the exercise is to prove that this quantity that you define here is actually a norm. Okay, so part one. This quantity here, which you may call it norm in the dual space. So this is a norm. This is not so complicated to do, right? I mean, this is a norm, it has to verify. If you multiply by lambda here, of course, the lambda will come out of the soup. That's fine. If the norm of a functional is 0, this means that the soup of L of x, when x is anywhere and the ball is 0, so all of these guys have to be 0, then it's easy just by dilation. So if L at the unit ball is 0, L at any point is going to be 0. So L is going to be the 0 functional because of the linearity. And then you have just to verify the triangle inequality. And the triangle inequality, essentially, the norm of L1 plus L2 is the supremum of L1 plus L2 of x. So you just are going to use that the supremum of two things loses to the supremum of one thing plus the supremum of the other thing separately. Okay? And the second part of this exercise is to actually prove that this space now, which is a normed vector space, is actually a Banach space. It's a Banach space. Yes. Exactly. Very good. In fact, for this second statement, you can even start with your x being just a, if you want, a normed. You can do the same discussion here with x being a normed vector space. Okay? And do the same thing here. And always your dual will be a Banach space, because the property that the dual being a Banach space is actually more related to the field of scalars being a Banach space. So everything that I said, let x be a Banach space, just forget, and let's just consider x being a normed vector space. You can do the same things. Okay? You will prove these two exercises here in this homework. Now, let's go back to Hubert spaces. And let's try to understand the situation there. So what we are going to do is that to prove that if this space X here is our LP, I want to understand what's the dual of it. So we will end up proving that the dual of LP is equal to LP prime. P prime is the conjugate exponent when P is not infinity. Okay? We are going to do today this theorem for L2. We're going to prove that the dual space of L2 is itself. We're actually going to do this for a Hubert space H. Okay, so now let's come back. So let's come back to our setup of Hubert spaces. So H is my Hubert space. Can you give me So an example, so a typical example of a functional of a bounded linear functional L. So in other words, L, an element in H star. Right? On H, okay? A typical example of a bounded linear functional L on H is the following. You give me, you fix a vector V in your Hubert space H, and let's consider this operator that I'm going to call LV on a point X. By definition, is going to be V is going to be X scalar V. Consider this operator. Okay, this is a map that sends. This is a map LV that sends elements in H into your field of scalars. C. This is obviously linear. I'm putting here X in the first coordinate, so because the inner product is linear in each of the entries, this is linear in X. And also, the norm of LV of X is less than or equal than, this is equal to the norm of the inner product, and by Cauchy-Schwarz, this loses to the norm of V times the norm of X. Okay? So by this, so if this has norm less than or equal than 1, you can pretty much find that the norm of LV is less than or equal than the norm of V. Norm of LV, this is in H, this is in H dual, okay? This is the norm of the functionals. So you get this. And moreover, you get more. If you take the element, just by taking the element X to be V over norm of V, which has norm 1, taking this element that has norm 1, you get that L of V of this guy, of this X, is going to be V over norm of V, scalar V, and this is going to be 1 over this guy is a constant, comes out, and then V, scalar V is the norm V squared, so this is just the norm of V. So you get LV applied on a vector of norm 1, attaining this guy. So, okay, so these two imply that the norm of this functional LV is, in fact, the norm of the vector V. Okay, so this is a typical example of a functional in a Hilbert space. You just fix a vector, and you take inner products with that fixed vector. Okay? Notice this inequality that appeared here. The norm of LV acting in a point loses to a certain number times the thing. This is pretty much a restatement of this. So this is the same as saying that, so if this is true, this implies that L of X, you know, this is a number. It's going to lose to the norm of L times the norm of X. The norm of L in here in the dual space, the norm of X here. Okay. Now here for any X, or any X in the space. Not necessarily in the unit ball. Okay. This is the same thing as this thing, just dilated. Okay. So what I'm trying to say is that this sort of typical example in Hilbert spaces is actually everything. So we are going to prove now the theorem called the Ris Representation Theorem that says that every bounded linear functional L on a Hilbert space is of this form, is the inner product with an element of the space. Okay, so this is the theorem of today's lesson for you guys to take home. Ris representation. let L from H to C or R be a bounded linear functional. Then there exists a unique element V in your Hubert space such that L of X is equal to X scalar V for all X in H. Okay. A bounded linear function is in a Hubert space is always the inner product with an element of the space. Take this theorem from the class today. Take this theorem. This is one of the theorems that you have to take from this course. Or maybe from your functional analysis course. I mean, you don't have to see these things that I am doing in this particular course. Some people see it before, some people see it later. But I wanted to do in the next class, if I can, a proof of the Radon-Nikodym theorem that uses this. There are other proofs of the Radon-Nikodym theorem, but I find this one that I'm going to present to you in the next lecture the most beautiful one. So, and this is Hubert space. This is actually, I think this is actually a simpler class than what we have been going through in this class. So this, everybody should be drinking your margaritas now and being relaxed. Let's see. Okay, so the easy part of the proof, let's prove this and conclude today. The easy part of the proof is that to prove the uniqueness. Okay, suppose you have two. Suppose V and V prime do the job. This means that X scalar V, so L of X, will be X scalar V will be equal to X scalar V prime for all X in your Hubert space H. But then you just subtract. So this implies that X scalar V minus V prime is going to be 0. Well, if X scalar V minus V prime is 0 for all the points X in your Hubert space, there is one particular point X that you can choose to break that. So now you just choose X to be equals to V minus V prime. And this will imply that V minus V prime, scalar V minus V prime, which is 0, but this is the norm of V minus V prime square. So this implies that V has to be equal to the V prime. Okay, so that's the easy part. So if this thing exists, it's certainly unique. Now we have to come up and produce an element, V. So I'm giving you the L. All that you know about the L is that it's a linear and bounded functional. It's a function that had the properties that I had here. So it's linear and it's bounded. I have to come up with this V. How do we do this? All right, so now the existence. So first thing, if L is 0, if L is identically 0, you take V to be 0. That's fine. If not, consider the kernel M. I'm going to consider the kernel subspace. M is the set of points X in your Hubert space such that L of X is 0. Set of points that are mapped to 0. This is not everybody, because I'm assuming that L is not 0. So L of there is a point somewhere that L of that point is not 0. So that point doesn't belong to this subspace M. Because L is bounded, because L is a bounded linear function, I argued with you, well, I told you to do at home, that a bounded linear function is also continuous. being bounded and being continuous is the same thing for linear functionals. So since L is continuous, this subspace M is closed. Okay, if you get a sequence of points xn in M converging to a point x, since the L of all of them is 0, the L at the limit will be 0, and this limiting point will belong to the subspace. So you have here a closed subspace. That's great. We're trying to get into a setup that we can use what we proved today. Now what we do have a closed subspace. So now take a point x that doesn't belong to M. We have argued that this M is not everybody if my L is not 0. So take a point x that belongs to H and not M. Take a point y that belongs to H and not M. Or maybe, let me call it x, so let me call this subspace of points y, such that L of y is 0. It's better like this. Take a point x outside of this space. So here is M, here's your point x. We are going to consider, as before, with the notation before, we are going to consider this point x minus the projection. We have seen that there is a projection. We have seen that x minus this projection is orthogonal to M. So let's consider this vector, let's call it W, to be x minus the projection. This is not 0, right? Because x is not in the space, so the distance is delta. So I can divide by its norm. So I am going to normalize it, so it's 1. So in the notation as before, this was the q of x over the norm of q of x. So take this vector here. So this is my W. Well, actually the unit. I am normalizing it to get a unit vector. All right. Okay. So now, let's do this. Now, let Z in your Hubert space be a generic point. Take Z be a generic point in your Hubert space and write, let me write U being another point in the Hubert space. Let's put it L of X, L of W times Z minus L of Z times W. Take a Z, any point in the Hubert space, and define this U being like this. So this is another point in the Hubert space, right? This is another point. It's just a number times this Z minus a number times this W. We have seen in the previous item that this W here belongs to M perp. Right? This is perpendicular to M. Okay. What do you know about this U that I wrote here on the board? Apply L on both sides. So apply your functional L. What you get is L of U is equal to, well, this is just a scalar. So this is L of W, L of Z, minus L of Z, L of W, which is 0. So if you apply L to this vector U, you get L of U is 0. So this means that this element U belongs to the kernel M. Well, if U belongs to the kernel M, this means that this U is perpendicular to my W, because I know that W belongs to M perp. Now let's just see what this is. So just take U and do scalar your W. So you get L of WZ minus L of WZ minus L of ZW, scalar W. This is equal to, this is equal to, this is equal to 0. Okay. And then what I get here is that the first guy, I get, this is a scalar, comes out, so I get L of W multiplying ZW. And the second one, I get minus L of Z, W scalar W, which is W square. But we have been normalizing W so that the norm of W is 1. So this is actually 1. And voila, this is what you get. This thing here is equal to 0. So if you move this L of Z to the other side, you find that L of Z is equal to this L of W, this number, Z scalar W. Now you can move this scalar inside there in the product. So this is Z scalar L of W bar W. So Z was a generic point in your Hubert space, and you ended up proving that L of Z was the inner product of Z with this vector that is fixed. W is fixed. So this is your V. Okay, you have found a vector such that L of Z is Z scalar V for any vector in your space. Okay? In this case, you have actually an isometry. We have seen that the norm of L is equal to the norm of this vector V. Okay? So this is actually an isometry, and it's linear. If you have vectors V, if a vector V1 corresponds to the functional L1 and a vector V2 corresponds to the functional L2, from the statement, it's obvious that V1 plus V2 will be associated to the functional L1 plus L2. Okay? So you end up finding a linear, a linear map, a linear isometry between H and H dual. So the statement is that the H star, the dual of H, is isometrically isomorphic to H. Okay. Yes. You're right. Okay. So this is the Ris Representation Theorem. This is what we take from this class today. So every bounded linear functional in a Hubert space is given by the inner product with an element of that Hubert space. Okay? So this concludes our class of basic notions about Hubert spaces. Let's do some exercises. We're going to use some of this in the next class. So the plan for the next class is to prove the Radon-Nikodym theorem and study a little bit about absolutely continuous and singular measures and how to decompose measures. All right, everyone. We finished the class here today. You all have a good weekend. I might send you some more exercises either today or tomorrow. Thank you all. Let's finish here.